In this video, I will talk about LMD Ghost, which is the fork choice rule at the heart of Ethereum's consensus. So, this is basically about when the network sees multiple valid chains, how does it decide which one is canonical? The name stands for latest message driven, greediest, heaviest, observed subtree. It was initially adapted from the original Ghost protocol by Zohar, and it was customized for Ethereum's proof of stake design. So, why do forks happen? In a distributed network, two validators might propose blocks at nearly the same time. Other validators see these blocks in different orders depending on the network latency. So, the result will be that a tree of blocks instead of a single chain that will exist. The fork choice rules job is very simple. So, given this tree and the votes from validators, determine which leaf block is the current head of the chain. So, every validator runs this rule locally and decides what to actually build on. Bitcoin uses the longest chain rule, which means always follow the chain with the most number of blocks. This is simple and works well for proof of work, but for proof of stake, the block production is fast and predictable, so the longest chain alone is not enough. The problem is that an attacker could privately build a longer chain and release it all at once, causing a deep reorganization or reorgs. So the longest chain ignores how many validators actually support each fork. So we need something that can count votes. So Ghost flips the approach. So instead of counting chain length, it counts the total weight of the subtree rooted at each block. So here weight means the number of attestations or votes for that block and its descendants combined. The algorithm starts at the genesis block and walks down the tree. At each fork, it picks the child whose subtree has the most total weight. It keeps going until it reaches a leaf, and that leaf is the head of the chain. Now, the LMD part. So, LMD stands for latest message driven. So, each validator casts attestations, which are votes for specific block, but validators can vote multiple times as new blocks appear. So LMD means we only count each validator's most recent vote. And why the latest? If we counted all votes, an attacker who controls one validator could cast thousands of votes in a malicious fork, inflating its weight. By counting only the latest message per validator, each validator gets exactly one vote. The weight of a subtree equals the number of distinct validators whose latest vote is for a block in that subtree. Now let's walk through the algorithm step by step. So we have a tree of blocks. Genesis at the top with two children, block A and block B. Block A has child C and block B has children D and E. Five validators cast their latest votes. So validator V1 and V2 voted for, let's say, block C. Validator V3 voted for block A. Validator V4 and V5 voted for block D. And let's say no one voted for block E. Now we run LMD Ghost. So start at Genesis. The subtree of A contains votes from V1, V2, and V3. That's weight 3. The subtree of B contains votes from V4 and V5. That's weight 2. So A is heavier. So we move to block A. At block A, there is one child C. We move to C. Block C is a leaf with no children, so we stop. Block C is the head of the canonical chains, and the canonical chain is Genesis, A, and C. In Ethereum, validators cast attestations every slot, which is every 12 seconds. An attestation contains the validator's view of the chain head and the latest justified checkpoint. So these attestations are the votes that feed into LMD Ghost. And these validators are organized into committees. Each slot, a committee of validators attests to the current head. Their attestations are gossiped across the network and included in future blocks. The more attestations a block subtree accumulates, the more secure it becomes. So LMD Ghost has some important properties. One of them is safety under synchrony. So if the network is healthy and majority of validators are honest, the protocol converges on a single chain. Honest validators will see the same votes and compute the same head. Next, it's resistant to balancing attacks in combination with proposer boosting. So the current block proposer gets a temporary weight boost in accordance with proposer boosting, which makes it harder for an attacker to keep two forks perfectly balanced. Third, it integrates well with Casper FFG. The fork choice only considers chains that extend the latest justified checkpoint. Let's consider reorganizations. So if a block arrives with more attestation weight behind it, the LMD goes switches to that fork. Short reorgs of one or two blocks can happen naturally under network delays, but deep reorgs require an attacker to control a large fraction of the validator set. And this is where Casper FFG complements LMD Ghost. So once a block is finalized by FFG, no fork choice rule can actually revert it. So LMD Ghost provides fast probabilistic confirmation, whereas Casper FFG provides slow absolute finality. I can create a separate video for Casper FFG later. So together, these two form Gasper, which is Ethereum's full consensus protocol. To summarize, LMD Ghost is Ethereum's fork choice rule. It walks the block tree from Genesis, picking the heaviest subtree at each fork. Only the latest vote per validator counts, preventing some sort of vote spamming. And combined with Casper FFG's finality, it gives Ethereum both speed and security.